This lecture is gonna be less technical and more conceptual, let's say. Previous 2 years, I was avoiding this topic because, well, sometimes it's too boring because, well, we are working with data, we are computing some numbers, we are having fun with testing hypotheses, and everything is very, very kind of nice and entertaining. Once we start discussing some conceptual things, once we start thinking about the meaning of the outcomes and something like that, people are immediately bored and their brains are turned off. But when I started working in data analysis, I immediately realized that this topic is one of the most important topics. Because, well, you can just press button, everything is gonna be computed, but then the question is, to what extent your results are valid and to what extent your results are showing what you really wanted to see. So that's why today we will mostly concentrate on the questions how the experiments are conducted and how you and where you need to be careful with this regard, because if you will try applying all the things we have discussed before in practice, you immediately get into some troubles with the interpretation, with the correct conduction of the experiment, with the correct way of collecting the data and so on. And if you really want to do something reasonable, if your results would cost to your company like several millions rubles or dollars, then of course you need to be very, very careful with these questions. So that's why today we are mostly gonna think, imagine, and come up with some ideas. Almost no mathematics and almost no estimation. But as I said, once I started working in this field, I realized that this is not just some theory. It's really, really important thing. Well, we know from the last semester that if we want to estimate causal effects, the best approach is to conduct experiment. And why we are studying all these things like OLS, instrumental variables, panel data, all the other things? Well, because in economics, it's not always possible to run experiments, and we need to work with observational data, and we need to find some special cases when we can estimate this causal effect without experiments. Why then we want to discuss experiments? So first of all, because even if you are working with the observational data, if you cannot run experiments over firms, over countries, over people, you still can imagine what is the ideal setting for you if you want to estimate the causal effect of some treatment, of some program on the desired outcome. It gives you some conceptual benchmark to compare with the practical application with the observational data. And what is more striking in this case, we never discussed this, that randomized control experiments are not ideal in the sense that they also have their own limitations and threat to validity. When you start practically applying all this randomization stuff and so on, you immediately run into some problems. And we are going to discuss these problems. And sometimes external events produce something which is called quasi-experiments. So we are going to discuss these quasi-experiments next lecture, or sometimes they are called natural experiments. When some disaster happens, like hurricane, earthquake, or something. So it happens at random, and it strikes people at random, or maybe some flood, something else. And we can use these settings as an experiment that the nature decided to conduct over people, or like tsunami. And sometimes this is also a nice environment for the randomization. Moreover, nowadays in data analysis, in business and marketing, we use experiments called A/B tests. And when it's possible to conduct, you are getting in the same troubles as the scientists who conduct experiments. You also need to be careful about all potential problems that arise with conducting A/B tests. That's why I decided to discuss these issues with you. Usually, we are going to talk about something which is called the program evaluation. So what is that? That's a field of study that concerns estimating the effect of a program, policy, or some other intervention or treatment. We will discuss the methods for evaluating social or economic programs. But if you want, those methods are not that different from experiments in the medicine, in pharmaceuticals, in physics, and so on. So the ideas of all experiments are the same. And in business, we also use the same methods for conducting experiments, with some limitations, of course, imposed by law, imposed by maybe corporate ethics, but you need to understand what is the ideal setting, what you want to implement. And once you understand what are the limitations imposed by, let's say, antitrust legislation, imposed by the crime code or something else, you will understand at least what are the ways how you can get to this ideal experiment as close as possible. For example, we can estimate what is the effect on earnings of going through a job training program. If you lose a job, or if you work and you go and the government, for example, funds some job training program. You have heard about this probably. You have received some notification from Gosuslugi site that government now helps to people who are unemployed, or who are I don't know, who has some like special category. So these people can, for free or partially for free, get a new job, get a new profession in the digital sphere, like digital marketing, data analysis, something like developers of mobile application, and so on. Is there any effect on earnings through after going through this program? Is there any economic effect for government from doing this? We can estimate this effect, or we want to estimate this effect somehow. Or the effect on unemployment of low-skilled workers of an increase in the minimum wage. So again, there is a government program, let us increase the minimum wage, and we also have heard about such steps taken by government. And then what is the effect on employment of low-skilled workers? Why low-skilled workers? Because for high-skilled workers, minimum wage, well, it's not relevant, right? So we don't care, like those who work on this higher skill job, they don't care about minimum wage at all. Basically, it concerns only low-skilled workers. Related to the business, and this is going to be particularly based on my recent experience, the effect on company sales of running a marketing campaign or a base program. When a company offers you some discount or offers you some kind of rebate. So what is a rebate? When you get some amount of money back. They are telling you, well, if you use, let's say, Mir card, you are gonna get like 5% of your purchases back. So how efficient is this for the company, and how to estimate whether it has some positive effect for the company? So those are just 3 examples of this program evaluation question. Now, a little bit of formal things, just to understand how this is constructed from the most ideal setting to the feasible setting, let's say. So suppose that you are offered a promo code with discounts by a big retail chain. We can ask, what are the benefits of receiving this treatment for you personally? Because you are treated. Somehow, the company decided that you need to get into this program, loyalty program, and you are granted with this promo code. Well, there are 2 hypothetical situations. One, first of all, you receive this treatment in the form of promo code, something like flyer, whatever, or you don't receive this treatment, you don't receive this promo code. And under each situation, we can measure some outcome that is gonna evaluate the necessity of the step. For example, one potential example, quantity of goods purchased. So how many goods you will purchase in this situation or in this situation. And conceptually, this is very important to understand the next idea. The difference in these 2 potential outcomes is the causal effect for you. So this is individual causal effect of the treatment. So basically, you are given this promo code, you are not given this promo code. You will, under each of these 2 treatments, or treatment and not treatment, there is some potential quantity of goods purchased. With the promo code, you go and buy like 10 units of something. Without the promo code, you go and buy 5 units of something. So the difference, 10 minus 5, is a causal effect for you. So this is called a potential outcome. So a potential outcome is the outcome for an individual under a potential treatment. It's not actual outcome, potential. And yes, the causal effect for the individual is this difference in the potential outcome if the treatment is received, if you have a promo code, and the potential outcome if the treatment is not received, if you don't have the promo code. This causal effect can differ from one individual to the other. Because if, for example, if I offer promo code to Vlad, and with this promo code, he goes and buy 10 units of whatever, Coca-Cola. Without promo code, he buys only 5. So the causal effect for Vlad is 5 units. I offer promo code to Vladimir, and he buys 15 bottles of Coca-Cola. Without promo code, he buys 13 bottles of Coca-Cola. So for Vladimir, the causal effect of this treatment is 2 units. So for each individual, the outcome is different. The causal effect is different. But here is the problem. There is no way to measure the causal effect for a single individual. Why? Because we never observe the same individual in two states. We cannot kind of produce a parallel world with Vlad and Vladimir receiving and not receiving promo codes for Coca-Cola. Right? So we observe only one state. For example, Vlad received promo code and Vladimir has not received the promo code. And this is the state that we can observe. And this is the problem. Because we really want, so this is our ideal case. In the ideal case, I want to compare Vlad with promo code with Vlad without promo code. I want to compare Vladimir with promo code with Vladimir without promo code. So I want to compare the comparable individuals. So the same individual. The problem is I cannot do this practically. It's infeasible. And then, instead of this individual causal effect, we go into something which is called the average causal effect. So the causal effect for a single individual cannot be measured. It's infeasible. Each person, each individual exists only in one state of the world. And for us, usually, it is okay, it is enough to know the mean causal effect in a population, not a personal causal effect. But ideally, it would be the best possible option. Because in this case, I can ideally target people with my treatment. I know who has the largest outcome, and I will be offering this promo code to these people, probably. But in practice, it's not feasible, and for us, it's okay just to know something on average, to know the mean causal effect in the population. And the mean of individual causal effects in the population under study is called the average causal effect or average treatment effect. So in our example, if I know that causal effect for Vlad is 5, causal effect for Vladimir is 2, so the mean treatment effect is 7/2, which is 3.5, something like this. For example, if you are talking about this marketing program, so the evaluation of this program might be based on comparing two things. So the average cost, how much price we reduced with this discount, with this loyalty program. And the second measure is the average benefit. How much was the increase in quantity sold multiplied by price. How do we estimate this average treatment effect? We know this. This is what we know from statistics from the middle of that course. This average causal effect theoretically can be estimated using an ideal randomized control experiment when we, first step, we select from the population at random the subjects that are gonna participate in our experiment. That's the first step. So suppose that you have all people in the country, and from this population you randomly select some sample of people who are gonna participate in your experiment about loyalty program. Then, well, you use simple random sampling. Nothing special is needed here. So the potential outcomes are drawn from the same distribution. So people are drawn from the same population, they have the same distribution. And the expected value of the causal effect in the sample is going to be this average causal effect in the population. Well, because of unbiasedness, right? So if I estimate the causal effect in a sample, it translates into the average causal effect in the population. Next step is to randomly assign my treatment, or randomly assign people selected on the first step to the treatment group and control group. So I randomly selected that, for example, from the Russian population, I'm taking, let's say, 10,000 people at random, and then I split these 10,000 people into, let's say, 2 equal parts, 5 and 5, again randomly, and 5,000 people are offered promo code, 5,000 people are not offered this promo code. This individual's treatment must be also randomly assigned. And the distribution must be, this is very important, must be independent of the potential outcomes. So I am not, we will discuss this later, but I am not offering promo codes only to the loyal clients. I'm not offering promo codes in front of Coca-Cola store. I'm not offering promo codes after asking, do you like Coca-Cola or not? No, I'm offering promo codes completely at random. I don't know who is this person. I don't know his or her preferences. I just know that this person is in my treatment group or control group. And then I distribute this treatment. This is ideal case. And you might ask me a lot of questions how in practice you can do this. And I would answer you that it is practically almost impossible to randomly assign this treatment. Because basically in this case, all people in our country must have the same probability of receiving this treatment or not. First, the same probability of getting into your sample, and second, the same probability of having this treatment or not. A person who lives in Irkutsk must have the same probability to get into this experiment as the person who lives in Vladivostok, in Moscow, in Kaliningrad, and in some faraway village in the middle of Siberia. If you think about this, practically it's almost infeasible. And we usually concentrate on some specific group of people, some specific population of people. If we are able to do all these things, then the expected value of the outcome for those who are treated minus the expected outcome for those who are not treated is going to be equal to the expected value of the causal effect. So a lot of words here. Now let's wrap this up in mathematical notation, because mathematical notation is usually more concise and more understandable. So all the things that we have discussed here. Denote a binary treatment, whether you are offered promo code or not, with x I equals 1. Well, I is individual. Some individual is offered this promo code, some individuals are not. Denote yi1 individual i's potential outcome if treatment is received. Look, this is potential outcome. This is one state of the world. What would be the outcome? So how many bottles of Coca-Cola would Vladimir purchase if he is offered promo code? This is not observable thing. This is a potential outcome of the same individual if treatment is not received. How many bottles of Coca-Cola would Vladimir purchase if he is not offered promo code? So in my example, this was 15, this was 13. But this is potential, hypothetical outcome. Now, the treatment effect of an individual I is this difference. The difference between two values. And once we talk about average treatment, we need to take all individuals and compute the expected value of these individual treatments. This thing is not feasible to compute, as I said, because we observe only one or the other outcome, but not both. So how mathematically we proceed to the estimation of something which is feasible? So this is our target. This target is not possible to compute. So what is possible and how our steps must be taken in order to accomplish this? Well, let us denote yi, which is observed outcome. And this is related to potential outcomes in the following way. So the observed outcome yi equals to the potential outcome if a person is treated multiplied by x, which is 1 in this case, plus the potential outcome of a person who is not treated times 1 minus x. If a person is treated, if x is 1, then the observed outcome equals to the potential outcome when the person is treated. If the person is not treated, x is 0, and the observed outcome equals to the potential outcome when the person is not treated. So very simple, and I guess this is a familiar notation because we use this same notation, or not the same, but similar notation when we constructed the alternative distribution. There was a power. We know that according to the design of our experiment, some individuals receive the treatment and some do not. And the expected difference in observed outcomes between the two groups is going to be this. So look, now I'm moving from potential outcomes to the observed outcomes. Look, this is observed outcome if a person receives a treatment given x equals 1, and then compute the expectation of this. And this is the observed outcome when the person does not receive a treatment given x equals 0. So this thing and the previous thing are not equal. But look, if I said, so now we are going to prove that if all the design of the randomization is correct, this thing, this difference, is equal to this difference, to our target. So how should we prove this? So first of all, first step is very simple. Once we know that x, look, instead of yi, I plug this expression. And if x is 1, I know that yi here equals to yi1. If x is 0, I know that yi here is going to be y0. So that's the first step. The difference between observed outcomes when x equals 0, when x equals 1 and x equals 0, so the difference between observed outcomes of the treated and not treated group equals to the difference between expected potential outcomes of the treated and control group. So as I said, potential outcomes are not observed. But with this help, we said that this difference equals to this difference. Well, this is true no matter how treatment is determined. I mean, at random or not, this is gonna be true. So the expected difference is the mean treatment outcome for the treated minus the mean no treatment outcome for untreated here. So those who receive the treatment, those who do not receive the treatment. And this is a potential outcome for one and for the other. How should we move from these to the initial expected value of the treatment effect, to this? So first of all, remember that individuals must be randomly assigned to the treatment and control groups. In this case, X is distributed independently of all personal attributes. Well, it means that X is going to be independent of Y1 and Y0, so of these potential outcomes. And once these two variables are independent, then what? Now we need to remember something from statistics. So this is the first step we did. Now the next step. If X and Y are independent, then conditional expectation equals to the unconditional expectation. Again, this is why it is very crucial to assign a treatment randomly, because only this allows us to put here this equality sign. Only when X is independent on Y of Y, this expectation equals to the unconditional expectation. And the last step is very simple. So based on the properties based on linearity of expectation, we know that difference of two expectations is equal to the expectation of the difference. So that's how, moving backwards from feasible thing to the not observed thing, we proved that making all the steps in a correct way, this, what we can estimate, equals to this, what we even are not able to observe. Yeah, so with the random assignment, this equality of conditional and unconditional expectation is established. And this is the crucial point here. So if X is, so this is in words, if X is randomly assigned, the mean difference in the experimental outcomes between the two groups is the average treatment effect in the population from which the subjects were drawn. So this is a formal mathematical proof why we need randomization. Because only with the help of randomization we are able to estimate what we are going to estimate. As I said, in many circumstances, this random assignment of a treatment is not possible. Now we move to the question, what then we must think about. So the first is the definition of a differences estimator. This thing must be familiar to you. In statistics, we discussed the comparison of two samples, of two sample means. And in that case, we established t-test for two means. Then we discussed in the first econometrics course the same problem but with the help of a single regression model with a binary regressor. So this is just another use of the same estimator, and we also give it a special name. Now this is not a difference in sample means, now this is a difference as estimator. So this is a difference in the sample averages for the treatment and control groups, right? This and this. This is observable, and this is the estimator for this, right? I just need to, so expectation is the population characteristic. And once I have a sample, once I have a data, I just change this expectation with the simple average. And calculating the average for the treated group minus average for the control group is exactly here. And this is called the differences estimator. Now, with the help of a linear regression, we build the following model. Xi is our binary variable representing the treatment. And then for the treated group, our effect is going to be beta 0 plus beta 1. For the control group, there is going to be just beta 0, so the causal effect is beta 1. If x is randomly assigned, again, then x and u are independent, so the conditional mean independent holds, and the estimator of beta 1 is going to be unbiased, is going to be consistent, and this is going to be the estimator of the causal effect. So beta 1 estimator with the help of OLS is going to coincide with this. So this difference, the estimator of beta 1 are going to coincide. We can improve this model with the tools that we have already discussed. If there are some control variables that help to explain variation in y, then we can include them. It is not because of omitted variable bias. It is to improve the efficiency of our estimation. They will reduce standard error of regression and consequently standard error of beta 1 hat. And in this case, our estimate is going to be more precise. This is one potential use of control variables in this case. If you remember, control variables were introduced in order to prevent omitted variable bias. But now, if you run a randomized control experiment, you can think, well, there is no omitted variable bias because everything is random, everything is independent of each other. Well, why should I include some additional variables? Still, if there is something that helps predicting y, you can include these variables into your regression because it will improve your estimation of the causal effect. Of course, everything that we have discussed before about control variables must be valid. It must satisfy the conditional mean independence. So it means that controlling for these variables provides that x is distributed at random. With the regard of experiments, Wi must be a pretreatment individual characteristic. So something that characterizes your participants before the treatment. For example, where is that? Yeah. If this is a pretreatment characteristic, and x is randomly assigned, then x is independent of u and w, and then this condition holds. W's should not include experimental outcomes. Nothing, because in this case, x is going to be correlated with w and everything fails immediately. Only pre-treatment characteristics. So the characteristics that have been already before you decided to run this program. For example, what's that? Gender, age, employment status, loyalty status of a customer, and so on. So everything that has been before the treatment can be included as the control variables, if you believe that this may explain the outcome. In our example, so I said that without a treatment, Vlad would consume 5 bottles of Coca-Cola. Vladimir would consume 13. So probably the loyalty of Vladimir to Coca-Cola is higher than for Vlad. And this is pre-treatment characteristic of a person. So we can measure this somehow, come up with some idea. Well, maybe initial initial consumption is not very nice, but we can, I don't know, create some binary variable of loyal customers and not loyal customers, or like frequent drinkers and not frequent drinkers. And then we can control this characteristic somehow if it helps us to understand the different causal effect, the different change in y. Or maybe gender, maybe something else. So it depends on which characteristic you believe can influence y. Even though x is assigned randomly. So formally, kind of you don't need to include control variables because x is random. But still, it is worth doing this because it will improve your estimation. More difficult and more realistic case happens when causal effects depend on observables. So we are moving closer to reality. So the variation in these causal effects might be different, and this is about the interaction of x of a treatment and w, the control variables. So for example, the effect of a discount on quantity demanded can depend on whether the customer is new or not. So if the customer is new, probably this customer is gonna be easier to attract with the loyalty program. If a customer is already loyal, then the causal effect is gonna be probably smaller. So suppose that Vlad is a new customer, he never tried Coca-Cola, and that's why his causal effect was larger, like 5 units. Vladimir is already a loyal customer of Coca-Cola, and that therefore the effect of discount was not that large, only plus 2 bottles. If this is the case, if you believe that this can happen, then you can include the interaction between W and X. And we have discussed this interaction term in one of the last lectures in the first course of econometrics. So if W1 is a binary variable 1 when customer is new and 0 otherwise, then the causal effect for new and all customers can be estimated, including the interaction term of this W and treatment effect. So even in experiments, we can apply these tools of nonlinear regression models that we have discussed before. And with this simple thing, you can estimate heterogeneous effects of your treatment. Another case that occurs in practice randomization based on covariates. If you think this case occurs very often. So when the probability of assignment to the treatment group depends on one or more observable variables W, then we have a case which is called randomization based on covariates. In this case, if you don't do anything, your difference as estimator is gonna suffer from omitted variable bias, even though you run randomized control experiment. But your randomization is based on covariates. To understand when this can happen, look, if again we have old customers W equals 1, but for example, you design the experiment in a way that your old customers or loyal customers receive treatment with less probability, with lower probability. So you are deciding to attract new customers, and you are giving them promo codes more often than to your old customers. So your experiment is designed in the wrong way, or vice versa. So suppose that you are conducting such experiment and you are distributing these promo codes in front of your store. Of course, people who appear nearby are probably your customers or your loyal customers. At least there is a higher chance than you will catch these people somewhere far away. So that's why your distribution of this treatment is going to be based on observable covariates. And in this example, when you want to attract new customers, and that's why you distribute these promo codes among them, well, suppose, as an example, your old customers tend to purchase more goods than the new ones. Well, this is reasonable. And then there is going to be omitted variable bias because X is negatively correlated with W. So look, your probability of being included into the control group or treatment group, let's say, your probability of being included to the treatment group of receiving promo code, this probability is larger when you are a new customer, when W is 0. So probability of X equals 1 is larger when W is 0. Negative correlation and immediately omitted variable bias. You are running an experiment. You just designed this experiment in a poor way, and your outcome is going to be immediately affected with this. Well, yeah, X is randomly assigned given W. So you randomly assign the treatment among new and old customers, but you're you have, so if you're a new customer, you have higher chance of getting this. And we can eliminate this omitted variable bias simply by including W in the regression, multiple regression model. And then if we include W into our regression, then the conditional mean independent holds, and the causal effect is going to be estimated in a correct way without bias. If there is a difference in treatment effect for all the new customers, again we can include the interaction term. But this must be taken into account. So let's say the ultimate message of the last 2 or even 3 slides is, even if you run a randomized control experiment, even if you want even if you think that everything is at random, still include additional variables into the regression because they will help you to avoid potential emitted variable bias if it still exists, even though it is a randomized control experiment. Still, there is a possibility that your design is conducted poorly. And even if X and W are independent, but W is able to explain something about Y, the quality of your estimation would increase. So, like, talking about practice. So we wanted to estimate the efficiency of our loyalty program with customers. And we distributed discounts among active customers. So those customers who showed up in last 3 months. We can immediately understand that this design is not purely random, because the probability of receiving this discount is higher for you if you are active customer of a company. If you are not active, if you haven't showed up for 3 months, you have a 0 chance to receive this promo code, or to receive to be included in the loyalty program, to receive a discount. So then we need to introduce this variable W that determines whether you are new or old, whether you are active or not active customer, and the effect is going to be probably different. So that's an important thing. And the next part is about threats to validity of experiments. So we spoke about threats to internal validity last time when we spoke about instrumental variables. What are the potential threats of to validity of experiments? Again, there is internal validity, there is external validity. Remember that internal validity is when your statistical study is such that statistical inferences about causal effects are valid for the population being studied. So, for example, in the case that I described you on the previous slide, we can say, well, the results of our experiment about the discount program are valid only for the active customers, for the customers who made their purchases within the last 3 months. This is going to be about internal validity. So this is only valid for this population. But still, we need to be careful when this internal validity holds. Failure to randomize. Very important thing. Failure to follow the treatment protocol. Attrition, experimental effects, and small sample sizes. So we will discuss each one in details. So what does it mean, failure to randomize? When treatment is based on the characteristics or preferences of the subject. So suppose the easiest case, we ask customers whether they want to receive promo code or not. This is a treatment which is based on preferences of the subject. Of course, the most motivated customers would ask for promo code. Of course, the least motivated customers, the neutral customers, the indifferent customers, or even those who hate our company, they would refuse of receiving the promo code. So that's why we cannot even think about estimating something like a causal effect. Because in this case, experimental outcomes would reflect both the effect of the treatment of giving the promo code and the effect of the non-random assignment, because the person has already been motivated. So probably the person wanted to buy our products, and so we just motivated him or her to do this with a larger quantity. Yeah, or the other example, as I already showed you, when the participants of this discount program show up in the store. So they already came to you, and if they demonstrated already the interest to your brand, their preferences could differ between treatment and control group. They are already interested. And if their willingness to buy differs with the preferences, there are going to be systematic differences between the treatment and control group. In this case, non-random assignment leads to the correlation between X and U, and we know what happens. There is going to be a bias in the estimator. This is even not an omitted variable bias. This is just a bias because we failed to comply with the first assumption of OLS. Well, good news. We can test for randomization. Once you conducted an experiment, you can test if your treatment is distributed at random. What should we do? X must be uncorrelated with observable pretreatment individual characteristics. So X must not coincide, must not be correlated with W. So for example, in our case, what we have done when we distributed these promo codes among customers, then we compared the proportion of males and females, the age distribution in each group, treated and not treated, distribution of regions where these customers come from, and everything else that we are able to collect. Ideally, you need to collect all pretreatment characteristics of these participants and compare. If you see that there is no significant difference between treated and control group regarding these individual characteristics, you are fine. You can hope that your treatment is distributed randomly. How can we use a regression framework in this way? Well, we simply regress X on these W's. And what verifies that X is not correlated with all observable characteristics? Joint F-test. We test that coefficients on W's from this regression are all zero. If this is the case, at least you are fine, you have avoided this problem. Failure to randomize. Very simple approach, but needs to be implemented. More difficult situation, failure to follow the treatment protocol. So people are not very good objects to experiment with, because people can partially comply with the treatment protocol or even don't comply with the treatment protocol. What do I mean? In the actual experiment, people do not always do what they are told to do. So you assign them to a treatment group, you probably tell them to do something, but they don't. In our case, the problem was that people can exchange their promo code. So, okay, you are given the promo code, we expect that you will go and buy something. But instead of this, you can share your promo codes with friends, relatives, and other people. Because you probably heard that your relatives are going to purchase some products, and you are so generous person and you shared this promo code with them. This is one story. Another story, that those who are assigned to the treatment group, they just forget about promo codes. You see that the person is in the treatment group, but you see that this person decided not to use promo code. Why? Who knows? So probably the person just forgot about this. And this is when the ideal world about ideal randomized control experiment fails to be implemented. And of course, if there is this failure, it leads to the bias of OLS estimator, because we cannot estimate the causal effect precisely. Ta-da! We know something that can help: instrumental variables. How can we use instrumental variables in this setting? The distribution of a treatment is gonna be used as an instrument. So the actual treatment of a person, so if a person actually used promo code or not, is determined by the assigned treatment level, right? So we need to remember who is given the promo code and who is not. And then we can compare these with the actual use of promo code by the person. And the assigned treatment level is an instrument because this instrument is valid. First, it is relevant. Second, it is exogenous. Relevant because it predicts the actual use of promo code, the actual follow the treatment protocol. And second, it is exogenous because we distributed this treatment randomly. So the instrument ZI is going to be the assigned treatment level. So the treatment level that you decided to be for this person. Again, that's how we can practically use our tools discussed in the previous lectures. So the instrumental variables here can help. Attrition. Attrition occurs when subjects are dropping out of the study after being randomly assigned to the treatment or control group. We just lose them. So it doesn't happen all the time and not for all experiments, but still you need to be careful about this if you really want to be aware of your experiment. So sometimes attrition occurs at random. That's fine. I mean, if just the person disappeared and you don't know what is the reason, no problem, because we are still working with something. There is an error term in our model, so this is an error term. But the more problematic case is when your treatment leads to this dropout, because there is going to be a bias in the OLS estimator again. So how it can occur? Suppose that the most loyal customers drop out of the loyalty program because they purchased everything they need. So they're loyal people. And if you are talking about something long lasting, like you are buying something like some electronic devices, refrigerators, TV, whatever. Well, of course, being a loyal customer means that you have already purchased everything, and probably the effect is gonna be lower, and you will probably even forget about this promo code and you will never use it. So our loyalty program led you to buy everything that you wanted, and then you drop out of the program. So what happens then? The least loyal customers would appear or would remain in our treatment group. And this will bias all our results, because we are working with, like, at the end of the experiment, we are gonna work with people who are less motivated, probably. So the distribution of this unmeasured characteristic, which is loyalty, will be different between the control and treatment group. And this would lead to the correlation between X and U and to the bias, which is called the selection bias. Now this is going to be the selection bias. What does this mean, selection bias? It means that people are choosing themselves whether to use a treatment or not. Sometimes this is a big problem. Your experiment changes the behavior of people, and consequently the results of the experiment are not valid. Another thing which doesn't occur all the time, so probably in A/B tests in business it does not occur because people even don't know about that they are participating in the experiment. But if a person knows about experiment and about participation in the experiment, then it can change the behavior of participants. It is called a Hawthorne effect. And there is a simple and elegant solution, which is called the double-blind protocol. So what does this mean, double-blind protocol, and why it is double? This is also another interesting thing. First, so subjects, and second, experimenters. So they know that they are in experiment. This is okay. So all must know that they are the part of experiment. But neither subjects nor experimenters know whether a subject is in treatment group or in the control group. Even you as an experimenter must be blinded, because in this case your judgment might be biased. So in our case, the initial distribution of a treatment has been done without us. When I analyze the results of this experiment, I don't know this person has been in treated or in control group. I know that this person is in group A. I don't know group A is treated or group A is control group. I know nothing about this. This is just group A. Compare the mean outcome with the group B. And then I publish the results and I tell, well, group A has the higher effect in terms of increase in sales than group B. And then the person who made this distribution of a treatment says, well, group B is a group who received the promo codes, so the promo codes don't work. I mean, this is an example. So that's how this double-blind protocol works. So experimenter must be also blinded. Well, if the experiment is double-blind, then both treatment and control group experience the same experimental effects. So regarding these experimental effects, as I said, in business, in A/B tests, this experimental effect even they do not appear sometimes, because people they are not aware that they are participating in experiments. When you open your mobile phone and some mobile app and you see some design, you don't know whether this is the personally created design for you, and you are now you are at the part of experiment, and then some other people are observing some other design, and then the data analysts of this mobile app are comparing some kind of like response time and time that you spent on the screen, something like the time to accomplish some goal on the screen and so on. You are not aware that you are the part of experiment. You are just doing something in your mobile phone, and people who are in charge of this, they collect all the data that they need. But sometimes these experiments are explicit. If you go for a vaccination, for example, you know that you are the part of experiment, and the experimental effect might be very large. So that's why all treatment and control group must be aware, and we hope that both groups experience the same experimental effect. And if there are different outcomes between the two groups, then we can believe, well, the experiment effects are the same for both groups, but if the outcomes are different, so this difference is exactly because of the treatment. Yeah. Often these double-blind experiments are simply not feasible. For example, promo codes. If you are given promo code, you know that you are a participant of experiment. If you are not given the promo code, well, maybe I even don't know that this discount program exists in the company. Yeah. Here, when you are not able to run the double-blind experiment, then you need to carefully think if there are some potential reasons to think that the experimental results are biased. You simply need to think how the experiment is conducted, and you always need to criticize the approach and think if there are some how to say, some problematic parts with that. The last threat to internal validity is small sample sizes. It's very simple. We are developing all the toolbox based on the assumption of large sample asymptotics. So we introduced this large sample asymptotics in statistics when we spoke about weak law of large numbers, when we spoke about central limit theorem, and we stated that when the sample size is large, we can approximate distributions of statistics with the help of a normal distribution and related distributions, t distribution, f distribution, chi-square distribution. If the sample size is small, so your estimator of the causal effect is unbiased if everything else is okay. But it leads, the small sample size leads to the imprecise estimate of the causal effect. It raises threats to the validity of confidence intervals and hypothesis tests, not to the estimator itself. Because, as I said, the inference is based on normal critical values and heteroscedasticity robust standard errors. And this uses large sample approximations. When there is a small sample, we cannot believe that the errors are normally distributed and we cannot apply the familiar tests. So that's why small sample size is not a very good idea. Collect as much data as possible all the time. Well, briefly, external validity. External validity means that inferences and conclusions from our population studied can be generalized to other populations and settings. So as I said previously, when we included in our study only active users, only active customers, then we cannot generalize the results of this study to the not active, non-active, or maybe new customers, because the setting is different and the behavior of these subjects might be different. And this is always need to be taken into account when some study is based on the United States setting. Maybe it is not valid for China. I was always surprised when American economists are trying to apply some American established models to China, for example, and they are so surprised that, well, in China it doesn't work. What's wrong with our models? Well, because your population and setting is different, completely different. There are cultural differences, there are economic differences, there are behavioral differences, and so on. So if you build your model on one population, it is not applied to the other population just because of this. So that's why be always careful with the external validity. Uh, Usually the population that you used to get your sample for the experiment must be very similar to the other population if you want, of course, if you want to project your results to the other populations. So what are the threats? Non-representative samples. Running a discounts experiment with only mobile app users. If you use only mobile app users and you distribute discounts among the mobile app students, so probably mobile app users, sorry, then probably your results are not going to be the same for the customers who are watching TV, who are getting the information about your company from some other sources. So if you get the results for one population, don't project, or be careful to projecting this to the other populations. Non-representative program. In the example that I'm using, it might be the following case. You want to get let's say, the silent response on your discount program during the experiment, and you use huge discounts, like unusually huge discounts that are not going to be used in normal time. Well, of course, your experiment would show the significant positive effect if you are given some large discounts like 95% of the price. But then, in normal times, you are going to have something like 10% discount, and 10% discount might not work because it's not unusual, and your program is non-representative. And of course, we don't need to forget about general equilibrium effects. So what does this mean? When your program is large scale and when it somehow involves the whole market, then with your experiment, with your program, there is a chance that market demand and supply, market forces and economic environment would change. And of course, it would change dramatically the outcomes. If you are running this experiment on the large scale, you are giving discounts. So it means that the price goes down. Probably the supply and demand curve would be somehow affected with this. You should be also careful with this point, not to run experiment on that large scale that it affects the whole environment. Well, this is, if you want, we are moving to the end of this first part of Econometrics II course. We are left with how many? We are left with one more lecture to conclude, and that's why I decided to kind of to get back to the initial question about randomized control experiments. So now we know a lot about observational data, about tools for working with observational data, and all the time we kind of refer to the randomized control experiment as a magical tool to solve all our problems. So now I decided to demonstrate to you that this is not a magical tool, and you always need to be careful how this randomized control experiment is established, even though you are able to do this. We must be careful with the design of the experiment and the implementation of the experiment, because sometimes the experiment itself can influence the behavior of participants in an unusual way and unwanted way. We need to remember about these threats to internal and external validity, of course. They are very important, otherwise your conclusions might be failed. And in the next lecture, before the midterm, we will discuss the question of quasi-experiments. So the setting that I described you, when some natural disaster happens or some other event occurs that is not predictable and can be treated as a random. You're very silent today, friends. Any questions? Any suggestions, ideas?
I want 15 Coke, please.
Me as well.
No,
What
you
about
want 10.
the midterm? I want the 20 right now.
Ты хочешь 5 без
I
промокода?
said you that the midterm is planned on
Okay.
31st of October,
In
right?
2
So
weeks.
yes, I guess, haven't I said it to you last time? I guess I said. Yeah, in 2
I
weeks.
forgot.
In the next lecture, I will provide you with the detailed information how the midterm is gonna be composed, what will be inside the midterm, what is not gonna be inside the midterm. So don't worry about this. Now, don't plan anything for this Monday after 2 weeks. This Monday 31st. During the lecture time, you will have a midterm. Anything else?
I guess no.
And good news. No quiz and home assignment this week.
Yay.
Thank you very much.
So we will discuss with Klim about your exercise session, what might be a good thing to do during that exercise session to maybe remember something from the previous lectures to prepare you to the midterm. So don't worry, there is gonna be something to do from the previous topics. I have heard that you are not very nice in discussing some theoretical and conceptual things during exercise sessions, so for you it's better to compute something. So we will come up with some idea what you can compute.
Interesting.
Okay, so then see you next Monday for the quasi experiments. Then 2 weeks after you have midterm, and then we start time series econometrics. Thanks for your attention and participation. Have a nice week. Goodbye.
Bye
Thank you
bye.
for the class.